We continue on the white dwarf theme. The next speaker is Rika, and she will tell us about one specific white dwarf, the first highly polluted, cool, hydrogen-rich white dwarf. Take away, Rika.
Oh, anyway. It's not working. It doesn't work. Okay. Okay. Hi, everyone. I'm Erica, and I'm a PhD student at the University of Montreal. On my day-to-day, I work mostly on polluted white dwarfs and debris disk around white dwarf. So today, I'll be speaking to you about a very, very, very old planetary system that we just uncovered and also discovered so many details about it in the last year. So I'll first do a really quick reintroduction on what are polluted white dwarfs. Then I'll talk into more detail about this white dwarf, how many elements we found, what do they tell us about the composition of the body being accreted, and finally, I'll do a quick recap and also tell you about what it means for the study of polluted white dwarfs. So as Laura previously mentioned, normally white dwarfs have pristine atmosphere of either hydrogen or helium. And because of the really high gravity of the star, if we see metals, we know that they come from an outside source. And we also know now that they are actually remnants of what was once a planetary system. And the objects could be asteroids, comets, whatever, minor planets. We actually have no really good grasp of how big these objects are, but still. But when we want to look for these remnants of planetary systems, we look specifically for helium-rich white dwarfs that have effective temperatures between 10 to 20,000 Kelvin. And this is really because of three key reasons. The first one being that helium-rich white dwarfs have way more transparent atmospheres than their hydrogen-rich counterpart. And so it's really easier to see the metals in the atmosphere. Also, at these temperatures, the helium-rich white dwarfs have way longer sinking timescales than hydrogen-rich, meaning that we have way more time to accumulate things in there and see them way better. And the third reason is also that the spectral lines of the interesting metals, namely, let's say, iron, oxygen, silicon, among others, these spectral lines are way stronger at these temperatures than hotter or cooler temperatures. So now that you're an expert in polluted white dwarf, let's ask the real question today. Who is LSPM J0207+3331? Well, it's a hydrogen-rich white dwarf, as it was spoiled from my title, but it has an effective temperature shy of 6,000 Kelvin. So you can really think of it as a mini sun. And I'll circle back to that as to why it's also interesting that it's really close to the sun. But yeah, and this white dwarf was discovered in 2019 by a citizen scientist who actually noticed that this star was way too red to what it was supposed to be. And as you can see from the SCD of the white dwarf, it has a really, really bright infrared excess coming from a circumstellar disk. And also, because the star is really cool, we know really well its age. So it is expected that this white dwarf has been a white dwarf for a little over 3 gigayear. But if we take into consideration its main sequence lifetime, we expect to be about a 5 gigayear old star. And finally, in 2019, when they published that actually initial discovery, they tried to model the SCD, the infrared excess, using a debris disk model, and they found that it was expected that the accretion rate of the metals in the photosphere would be of the order of 10 to the 7 grams per second, which was enough to request some follow-up with high-resolution spectroscopy, which is really polluted white dwarfs' bread and butter. So this is what I'm really here to show you today. So we have the case of a really, really, really polluted white dwarf with a total of 13 metals discovered. And also what's really interesting is that we discovered strontium in the photosphere of this white dwarf, which has only been discovered in like 2 or 3 other white dwarfs before. So this is really new also. And what we think is that maybe strontium is easier discovered at cooler temperatures. And if we want to really have an idea of what extrasolar strontium looks like, we might actually need to look for cooler white dwarfs. And another really interesting thing that we found is that in the core of the calcium H and K lines, we kind of see a glimpse of core line emission, which is usually a marker for stellar activity in main sequence stars, but it's a dead star, so not really here. But we don't really know what's happening here because it's only the second time we've found this in a white dwarf. The first one being a helium-rich white dwarf that is way hotter. So we don't have a reason. There's not much in common apart from metals. So one hypothesis is maybe accretion heating. So at the really upper atmosphere of when the metals get accreted, there's maybe some heating happening there, and we see it here. Yeah, and so now that we've modeled the spectrum, we can now extract the abundances. And so for this one, if we compare our abundances with, let's say, bulk Earth, which is the green shaded area in this plot, we see that there's really an enhancement in refractory elements. And so that means that we have something that is more a core-like material, whereas let's say a crust or a mantle or just a general bulk Earth composition. So that also confirms that this rocky object was differentiated, and now we're just kind of seeing more of the core of that object. So that's really interesting. And so back to the mini-sun part, so because of the really well-known solar spectrum, we know that at these temperatures, we expect to see molecular CH in the optical. And we use that fact to actually derive an upper limit of carbon, because usually we just see it in the UV. And so now we can really look at, well, if we have really cool white dwarfs, we actually don't need the UV to have to probe carbon in our abundances. So that was really interesting. And it also helped to really actually eliminate the idea that it was a carbon-rich material. So what's cool with this really old field that is white dwarfs is that we know really well the physics of the atmosphere of white dwarfs, and we can extract actually the mass of the metals that are in the atmosphere. And if we take just an average density of an asteroid, we get an object that it has a radius of about 150 kilometers. But for this specific white dwarf, the sinking timescale of metals is about 100,000 years. So it's really a reasonable assumption to say that probably more metals have sunk below the photosphere. And with that in mind, we actually think that the object is probably above 200 kilometers in radius, which starts to be a really interesting radius to known objects in the solar system, such as moons and minor planets. Then we also measure the accretion rate. So we get something to the orders of 10 to the 9 grams per second, which is 2 orders of magnitude higher than what was calculated with the debris disk itself. So it's really, really huge. And it's one of the highest accretion rates that we've ever measured in a polluted white dwarf. And so in the recent years, some people have speculated that maybe as the white dwarf ages, we should see a decrease in accretion rates, similar to what we see, in main sequence stars. But so we don't think. So when we do an actual plot of these, we see that there's no really obvious trend. And I can maybe just use that to show you. So the initial authors says, well, there's a decrease like that, but not really. And then actually having LSPM added to the plot really plays into that scenario that there's no obvious decrease. And yeah. And so now I want to finish this talk with a short bedtime story about this system. So 3 billion years ago, an A or F-type star died, and its remaining core became a white dwarf. And nobody knows what happened to its planets, if there was an asteroid belt or anything really. We just don't know. Then 2.9 billion years later, which is really yesterday for this white dwarf, a mysterious phenomenon perturbed a minor planet, and that planet reached the Roche radius of this white dwarf. And this led to the destruction of this minor planet, which is tragic, but you know. Then, after a few million years, after the planet was fully disintegrated and formed a really gorgeous debris disk, these debris started to be accreted by the white dwarf, and this is what we see today in the atmosphere. And yeah, so apart from what we see in the atmosphere or in the disk, we'll never know what that system really was and how prolific it was as a system. But at least we are lucky enough to see it before it completely dies, and we can't really see that there were planets here before. Thank you.
All right, great talk. Questions? Okay, we have one here. Yeah. Oh, here. Yeah.
Hey, this is very interesting. I had a question about your bedtime story.
Yes.
So I think you mentioned you don't see any time variation of these elements. Does that mean that the accretion is still going on, or are you sure that it stopped? Is there still a little bit of stuff that's still falling into the white dwarf?
Yes, so there is still stuff happening. And so, yeah, because actually we see the disk, we usually make the assumption that it's still coming in. So if we measure, let's say tomorrow, we do another spectrum, we'll measure the same thing, because it's really, there's not a stark difference. And the disk already still exists, so yeah.
One short question before we move on.
Thank you, Erica, for sharing your enthusiasm.
Can you speak louder, please?
Thank you for sharing your enthusiasm. That was great. I had a question. You don't necessarily need to go back to the plot, but the plot on the abundances, you mentioned that you thought this might be some core-like material. So my question is related to that because it looked like the lithophilic elements, aluminum and calcium, are also elevated.
Yeah.
So have you considered the possibility that it's just silicon that is poor, because that's what sets the scale for your entire element? And it looks like—
Sorry, I missed a bit of the sentence.
It looks like, have you considered the possibility that the object is silicon poor? Because that's what sets the scale, and all of your elements are above, including the lithophiles, which you would expect with the crust. So does that make sense?
Yeah, I'm not the one who did that part, so this is actually Laura's work. But
okay, no problem, no problem.
But we chose silicon because it was actually a more neutral element to use and to really get to extract that information.
I just meant that there were lithophiles that were also elevated, which is not what you would expect with a core. That's all. Thank you.
All right. With that, let's thank Erica again for the very nice talk.